Okay. Good morning. So I hope to get to the eta prime story now, and it's probably useful to, because there is some analogy, actually pretty deep connection with the story of this screening of the electric field in 1 + 1 dimensional Schwinger model. In certain sense, this 1 + 1 dimensional model is simpler, so it's good to a little bit refresh the memory, okay, about that. Oh, this line is going up, right? So very good. Okay, so let's start with 1 + 1 dimensional electrodynamics, okay? Actually, there is, if we only have, as we said yesterday, we only have a vector potential that doesn't propagate any degrees of freedom, but it's a Maxwell-like theory with a Lagrangian, which we can just write down for just like Maxwell Lagrangian. We can couple this to an external current. And if we investigate this theory exactly the way we did standard electrodynamics, 3 + 1 dimensional, of course it exhibits gauge redundancy and everything. There is a gauge redundancy, and we can use this gauge redundancy to fix the gauge and eliminate first 1 degree of freedom by fixing this gauge, and then eliminate the 2nd degree of freedom. And so I will not repeat the story. It's identical to 3 + 1, and so we are left with something that doesn't propagate degrees of freedom. Okay, but it's still, of course, it's still physical because it can respond to the sources. Okay, first, and secondly, it also allows a constant electric field solution. Okay. Now, for instance, if I choose a source to be a particle of charge q localized, let's say, at some point x = 0, so I can choose the source in this form, right? So q delta of x. Okay, we have 2 coordinates, x and t. Now here we can rewrite, as we did, I think we did yesterday, as a scalar function. Okay, it's not a propagating scalar; it's just a scalar function, or which is the same, would be 1/2 of. Okay, and so using this, so you can see immediately, right? Because you can see immediately that the equation of motion are, since the equation of motion are epsilon mu nu acting on F is this guy, right? Q. So there is a jump at the location of the charge. Okay, so there is a signature function, right? So a step function. Plus a constant solution, right? So therefore, F is a signature function controlled by the Q, and then there is a constant part which we can call theta. Okay, so there is a constant background electric field solution. Now, if I ignore charges and simply consider my vacuum solutions, right? So if all charges are heavy, then the vacuum is characterized by an arbitrary constant electric field. Okay, so we have a continuum of the vacuum states, and we don't have transitions. Well, we can have transitions with the step q if we have heavy charges, okay, but I mean there are only limited transitions. Okay, and so we have this different super selection sectors, okay, so which are labeled by theta. Now, your choice of the vacuum is your choice of theta. Of course, here I'm working in units because by the way, in 1 + 1 dimensions, the A mu is dimensionless. Okay, so field A mu is dimensionless. So the F has canonical dimensionality 1. So okay, we have to work in some mass units. Correspondingly, charge has dimensionality of the mass, and so on, right? Okay, so now if I expand my theory, so I choose my vacuum and then I expand my theory on top of this vacuum, right? That's what we normally do. If I expand my theory on top of the vacuum, then the theory expanding on a vacuum, although there was no theta term here in the original theory, it will acquire a theta term. I think with a factor of 2 or something. Okay. Okay. So this is one story. So in other words, the choice of the so notice the following thing, right? And this is okay. This is not semantics, because I could have from the beginning introduced this as a parameter in the theory. Okay, right? But actually, the moment I introduce is not a usual parameter from this point of view. Because when I introduce a parameter in the Lagrangian, let's say an Yukawa coupling constant of the electron, etc., I don't consider other superselection sectors in which Yukawa coupling constant of electron is different, unless I really have a field which changes and it gives me different values, etc. Right? So it's a parameter in the Lagrangian. Here, what you could introduce as a parameter in the Lagrangian, in the same time, is a declaration of your choice of the vacuum. Okay, right? So it's a parameter that parameterizes your choice. Okay. Now, you can also understand this from the following fact. Suppose I start with this as a parameter. Okay, right? Okay, I start with this as a parameter, but I can rewrite this as a charge located at the boundary. Okay, right? So I can think of this as coupling of A mu to a current, and this current describes boundary. Okay, so it's sorry, this is okay. So this is little x is our coordinate, big X is the embedding of the boundary. It's the history of the boundary in the space, and xi is the proper coordinate, word volume coordinate on the boundary. In this case, there is only one. Okay, right? So now this way of writing this, so therefore this is effectively that. Okay. So in other words, in the same time, you see immediately that boundary term defines the background electric field. Okay. And that's why you see different vacua with different, and they are physically different because of parity properties. The parity properties are different. Okay.
You choose the vacuum, right?
I have to choose the vacuum. That's right.
But how come? We can see the fields classically, right? So there's no quantum correction.
Yeah, this is also true. If you don't have charges, or if charges are very heavy, you can. If you have heavy charges, you can have transitions with the step Q. If you have no charges, then simply you don't have any transitions. So that's why they are super selection sectors. These are literally like theta-like vacua. It's not exactly theta vacua, but theta-like vacua. No, there is no axion at this point. We'll now get to the axion. So far, this is like, it looks like vacua in pure QCD, or QCD without axions and without heavy quarks. Sorry, without massless quarks. Okay.
What happened with the previous charge, where you just?
No, previous charge could be there on top of this. In other words, I can have this This is boundary. I don't know if you want to let's give it a let's give it an index B, and you can have other charges on top of that. Okay. Now,
but what you say in the selection of the vacua says the boundary condition on.
yeah. In other words, they are interrelated. In other words, okay, this may sound a little bit semantics, right? Because you can say, okay, who cares? Let me call it a parameter. But it's good to understand what does it mean to have a parameter. This parameter parameterizes your choice of the vacuum. Okay, they are linked. The moment you wrote this parameter down, you declare that you want to choose a particular vacuum among these. So there is one-to-one correspondence. That's what I mean. Okay.
And why J does not depend on theta?
No, theta is the solution. So if I started with forgetting about boundary, and I said, okay, let me write down an equation. Let me assume the boundaries are not important. And I found a solution with this, which gives me jump. This is local influence of the charge. And then there is a constant background solution, which is independent of that. That's what I call theta.
Okay.
Now, this constant background solution, when I plug it back, so the constant background solution tells me that I have to make a choice, because you have to tell me on which vacuum you want to work. Okay, so you made a choice. You choose your theta, and then you say, okay, let me plug it back and expand around this theta. My theory. Yeah, you get this term. You get this theta term. Okay, but you could have started without this song and dance from the beginning. You could have written this term, right? If you would write it from the beginning, it would look like simply a parameter. But this procedure tells you that it's not really a parameter. It's a parameter, of course, but it's a parameter that gives information about your choice. Okay?
That part I understood.
Right.
Why there is no theta inside J? You said.
Sorry, this is theta. Sorry. Oh, I'm so sorry. Yeah, this is theta. That's the whole point. Yeah. No, thank you. It's not Q. Yeah, please. Q belongs to the local charge. Sorry. Yeah. That's the whole point. Otherwise, this would be useless. So yeah, Q is the local charge. So the Q controls this step, and then there is theta. And theta you can rewrite as a charge carried by a boundary. Okay? Right, thank you. Yeah, very good. So you should control me, you see? Otherwise I can say something completely crazy. Yeah.
And so there's no way to, is this if only is if statement, there's no way to separate them. If you have that frame?
Yeah, if you don't have, no, there is a way to separate it. They are physically different. That's what I'm trying to say. So these are different vacua, literally physically different. Yes. An observer could measure them, okay? So the only thing, the restriction here so far is that I don't have massless charges. If I have heavy charges, I can measure them and say, and this is physically different. And yeah, that's right. But there is no way to transit from one to the other.
Okay, so if you write the parameter in your Lagrangian, you make the vacuum choice. If you make the vacuum choice, you have the parameter.
Exactly. There is one-to-one correspondence that every time you write a parameter, you can interpret it as a vacuum choice, and every time you make a vacuum choice, this results in your parameter. Right.
And this is generalized during 1 plus 1. Is it going to generalize to 3 plus 1?
Yeah, in 3 plus 1, this generalizes to normal theta vacua. There you know that theta vacua is precisely about the choice. You have many and you have to choose one, right? And that choice is parameterized by the parameter that you include in the Lagrangian, okay? Okay, so now again, let's assume that we have an observer that lives in this 1 plus 1 dimensional theory and then knows the story, knows physics about this stuff. Now, this observer would expect that there is some background electric field in the universe of this toy observer, right? Because okay, there is a continuum of values and there is one special value 0, right? Okay, so y should be 0. Now imagine this observer wakes up and sees that actually this theta is 0. This background electric field is 0. Okay. Now this observer will start to look for a dynamical reason behind this, why this field is 0. Of course, it could be a coincidence. It may happen that somehow, since these are different super selection sectors, Okay, one attitude could be that we should not even ask this question, because since there are no transitions, etc., there is no dynamics that takes me from one to the other. Just live where you are, and that's it. But there is also a very nice dynamics that could accomplish this. Okay. Now, in 1 + 1 dimension, these dynamics you can introduce in several different ways. The simplest one well-known thing is that you introduce fermions that are massless. Okay. So what happens? Now, if I introduce fermions, let's introduce some fermions. So let's introduce massless fermions. So there is a current, which is vectorial current in this theory, and this current is sourcing a mu. Okay. Now, in this case, what happens? And we mentioned this briefly yesterday. Okay, because there was a question. What happens in this case is well known, that the contribution from the fermion loop generates a mass, effectively, for this. For a mu, and so what happens is that if I integrate out fermions, there is a following structure that I get. Okay, so this is a transverse projector that appears here, and now you see immediately that this structure, this structure effectively generates a mass, because let me remind you that f mu nu, right? You can rewrite it as up to partial integration. It again has this form of a transverse projector, so it has a form of, sorry. Well, it looks non-local, so we'll get there. Yes, absolutely. Sorry. Sorry. Yeah. Okay, this is this thing. So effectively, what you have effectively the action looks like box. Plus m plus e square over pi p nu a nu. Okay. Now, and there is a pole at p square equals e square over pi, and so we have generated a mass for the photon, right? But let's try to understand. Yeah, I'm getting there. You mean about?
No.
Yeah.
What actually happening? Are you introducing this effective action?
Yeah, I'm just saying if the effect of I want to understand how the one loop correction. I'm not like writing the full effective action. I want to understand how the one polarization because of the photons pair creation of the photon pair creation is modifying the dispersion relation, how it's shifting a pole at p square equals 0. So before we had a pole at p square equals 0, although this pole was not propagating, but was a pole, okay? And now this pole is getting shifted, okay? And now I'm trying to understand what does this mean, right? Okay, now, of course, this means that there is some mass generated because we no longer have a pole at p square equals 0. But let's try to understand what happened, okay? All right? Now, notice the following thing, that this type of effective action, this type of effective propagator or bilinear part of the action, I would get in our Proca theory if I would integrate out a Stuckelberg field, okay? Right, so let's see, right? So in Proca theory we had, so let's write down Proca generalization of 1 + 1, okay? With m square and I would have a Stugelberg field. Let me call it B, okay, because I want to make connection with B mu nu, and that's why I'm calling it B, little b, okay. All right, and now I want to integrate out B, okay, right? So we can integrate out B through its equation of motion, which is simply d mu of a mu minus box B is 0, and so B is d mu. Okay, now if I integrate B and plug it back there, all right, what I will get, or plug it in the bilinear in the action, or plug it here. Okay, what I'll get exactly this action. Right? You can easily see that. So we get precisely this thing. Oh, sorry, let's write it together. Yeah. Yeah.
Maybe I'm a bit lost, but
Yeah.
actually when you have QED and you integrate out fermion.
Yeah, you mean in 3+1? Yeah, in 3+1 it doesn't happen.
You have an organization of the charge fields, right?
Yeah, in 3+1 this doesn't happen. This is a peculiarity of 1+1. We'll see it immediately. We see it now why. There are many reasons why. Because 1+1 is not 3+1. That's of course true. But this peculiarity of so in other words, you see. Yeah, this is good that you're asking this question. So, okay, I want you to give physical interpretation a little bit later. But how can you think about it physically? It's like to give a mass to a photon means that you are screening the electric field, right? Okay, so now, how do you screen electric field? You can screen electric field by polarizing the medium, right? So, for instance, if I have real charges floating around, massless charges or light charges, mobile charges in the superconductor, for instance, right? In superconductor, electric field gets screened. Why? Because it mobilizes charges, and so they are mobile and they screen the electric field. Now, what happens in the vacuum if I don't have charges around? Okay, if I don't have charges around and charges are massive, obviously, if I go below the mass of the charge, their effect is unimportant. Okay, even the virtual charges no longer are very, very important. Okay, but if charges are massless, right, then at each, no matter how far I go deep in infrared, there is a polarization of the vacuum. Okay. Now, this polarization, so the question is whether this polarization is powerful enough to screen your electric field. Okay, now this polarization can do the different effects. It can renormalize your charge. Okay, so in other words, it contributes into charge renormalization and charge runs. And as we know, in 3+1 dimension, there is a highly non-trivial phenomena of this with massless fermions, and actually infrared QED, infrared QED is a pretty interesting story, right? But here we are talking about generating a mass for the photon. Okay, so in 3+1 dimensions, this virtual polarization of the charges that electric field can take out of the vacuum, okay, is not powerful enough to generate a mass for the photon. Okay, so what happens in 3+1 is the photon remains massless. Of course, there is some partial screening or anti-screening effect, depending whether you are in asymptotically free theory or whatever. Okay, in U1 is not never asymptotically free, as you know. But that's it. There is no generation of the photon mass. Somehow, what happens in 1+1, because of codimensionality of the charge, this is important. Okay, so what happens is that charge, if I have a point-like charge, in 3+1 it has codimension 3. Okay. And it's not powerful enough. The effect of the charge is not powerful enough. In 1+1 dimensions, there is too little space. There is only one space, and therefore the effect of the charge is actually infinitely important, because the electric field created by the charge, as we see from there, is simply a constant. It doesn't even decay. Okay, so you can Okay, you can intuitively trace these differences to this type of properties. Okay. Now, but coming back to this, so you see what happened is that this theory that we go, this effective part of the theory, okay, this the bilinear that we got, is fully equivalent to a 1 + 1 dimensional Proca theory, in which I'm only considering processes in which Stuckelberg appears as an internal line. Okay, because integrating out Stuckelberg, what does it mean? It means that I'm only considering processes in which Stuckelberg is appearing as an intermediate state. Okay, right? So this is what we're getting. So somehow what happened is that massless fermions, they provided a Stuckelberg. And this is not what is happening in 3 + 1 dimensions for the electromagnetic field. So for the electromagnetic field, massless fermions in 3 + 1 dimensions cannot provide a Stuckelberg field. But massless fermions in QCD, as we will see, they do provide Stuckelberg field to screen theta analog field that is analog of this electromagnetic field for QCD vacuum. Okay. Now we can play around with this. Yes. Yeah.
There was a paper in 2013 by Dvali and He that said that there is a possibility for a very small Stuckelberg mass for the photon. Very small.
Well, let me make it very clear. Stuckelberg mass for the photon is simply a mass for the photon. There is no difference between mass of the Proca mass and the Stuckelberg mass. Okay, so this is, I want to make it very clear. Stuckelberg is just the way to understand this mass. Okay, now there is a bound on the photon mass. I can tell you what is the bound. If we are talking about real photon, okay, I'm detouring now from the subject, but yes, I mean the question of the bound on the mass of the photon is a very interesting question. It was assumed that the bound is very severe. It was coming from the galactic magnetic field, because somehow the assumption was that if we are in a Proca theory, the galactic magnetic field would be different from Maxwellian because of the mass, and so therefore the bound on the photon mass that is I think it's still cited in particle data group. I didn't check it, but is something like inverse galactic scale. Okay, I think 10 to the minus 27 electron volts or something like that, right? Now that's a wrong bound. We showed that with actually we have a paper with 2000 something, early 2005 maybe, I don't remember, with Eric Adelberger and Andrei Gruzinov. So we showed that if you generate photon mass through the Higgs mechanism in the standard model, of course you have to add some new particle which has a minuscule charge and this kind of stuff. That's not the correct bound, because what happens is that with the Higgs mass, because Higgs mass is soft, so the galactic magnetic field can adjust itself and be practically Maxwellian. There's a huge parameter space when it could be practically Maxwellian. So I think the most severe bound on the photon mass is coming from direct measurements of the Coulomb law and probably deflection of the starlight. Maybe gravitational wave versus this thing now is improving that. I don't know. I don't follow this later. But that bound is way less severe. It's approximately something like 10 to the minus 17 electron volts or 10 to the minus 14 electron volts. And 10 to the minus 14 electron volts actually is nothing, because if you think about it, that's an Earth-Moon distance. And it's really incredible that we don't know the photon that we have all around, right? We don't know it better than Earth-Moon distance with the Compton wavelength. Okay, but sort of that's the story with photon mass. But of course, this has nothing to do with real photon. Let's come back to this imaginary 1 + 1 dimensional story. Okay, now we can play around with this picture. Dualize it. By the way, did you dualize what I told you from B mu nu to go to there? You can do it as this is just a simpler version of this. Okay, we can dualize by taking dB as a fundamental form. I can declare that this is fundamental. I can call it, what should I call it? Let me call it, I had a good name for it, but then I forgot. Let me call it Q. No, Q is not good. Okay, let me call it Y of mu, right? And So we can do exactly the same thing. So in other words, replace this with y of mu in the Lagrangian here. So replace this with I leave this term as it is. Replace this with y of mu, and then impose Lagrange multiplier constraint that to take into account that this is a one form, okay, which will look like as epsilon mu nu d mu y nu, okay. And that's it. So now you can write down equation for A imposes the constraint that equation for A imposes the constraint that epsilon mu nu d mu y nu is 0 because this is a one form. This is a derivative. And then there will be equation for the rest of the equations, and we can solve for y and plug it back, and we'll get a theory that we wrote yesterday. So we get a theory in which we have, if I switch to these notations of f, we get a theory in which we have something like f square, then plus a of f, a times a divided by f. A will not have canonical dimensionality. If we need canonical dimensionality, we have to divide it by something. And then, sorry, other way around. Here it has canonical dimensionality and something like that. Okay, so we get this theory. So if I just plug it there, I dualize, I get this theory. Okay? Which, again, shows in a different language that fermions, massless fermions, they provided a Stuckelberg field, okay, for the gauge field. Okay, so now, yet another way to understand this effect. Maybe this I can erase. Yet another way to understand this effect is through the anomaly. Okay, so in one plus, so there is a current. There is an axial current. So there are two currents, axial and vector. Okay. Now at the tree level, they are both conserved. Okay, but at the loop level, one of them is no longer conserved. Okay, so we choose to be axial. Okay, the axial current is not conserved, and so there is a one loop, which is a sort of a partner of this diagram. Okay, and that generates non-conservation of the current. Exactly, very similarly to what happens in anomalies in 3+1 dimensions. Okay. Sorry. And okay, so non-conservation has this form. Okay, so now, okay, there is this anomaly. Why this anomaly is generating mass for the photon? Because in 1+1 dimensions, we have relations between axial and vector currents, which we don't have in 3+1 relation, 3+1 dimensions. What is the reason for that? The reason for that is that the properties of the gamma matrices in 1+1 dimensions. Okay, so in other words, the axial current and the vector current are related. And this has to do with the properties of gamma matrices. Okay. And so therefore, we can use, so this is one anomaly equation, okay? But then we have also equation of motion, right? So equation of motion is normal equation of motion, coming from this, taking just simply equation of motion for the photon. Now equation of motion is telling me that there is that the electromagnetic field is sourced by a current, right? Which is of course, I can rewrite as with our convention, F E times J nu, but J nu I can express as the axial current. Okay, so therefore there is another relation between axial current. And then now you can take this equation and this equation. You can exclude axial current from this equation, and you can see immediately that you get an equation okay, so what happened? Again, the same thing happened. It's just another way to see the same effect. F became a propagating massive scalar degree of freedom. Okay? So all these languages are the different parts of the same story. Okay? They are all interrelated. Now the final link we can make, just remembering that because of these properties because of very special properties of 1 plus 1, in 1 plus 1 dimensions we have bosonization. Okay? Bosonization meaning that the fermions, what did I write? Okay. Yeah, okay, let's see it like this. There are relations between fermions and scalars. So in other words, sorry. And so on. Now, there is these bosonization relations in 1 plus 1 dimensions that are known independently, okay, have nothing to do with whether you want to generate mass for the photon or not, okay. It can tell you immediately that if I use these relations here, I will get this immediately, okay. So, okay, so now, let's summarize a little bit, okay. So what happens in 1 plus 1 dimensions is that we have an analog of the theta vacuum choice, okay, which is reflected in the fact that there is an electric field, okay, background electric field. Now, why this is not completely semantics? What this question whether it's a parameter or it's a vacuum choice? Because this is a boundary term, right? Okay. Now you say you put a parameter in your theory, okay? The same is true in QCD. I put a parameter in my theory, and this parameter is a boundary term, okay? Now think in terms of physics. How good boundary term that is on a boundary could make a locally observable physical effect? How is that possible? Huh? No, I understand instanton, but instanton is just a code word for how is it possible? In other words, there must be a messenger. Yeah, there must be a messenger because boundary term is something that lives on the boundary, right? There must be a messenger that somehow brings the message influence of this boundary term locally so that I can measure it in laboratory, okay? Right? Now, this so in general terms of, okay, sure, instantons is one way, but here we don't have instantons. Okay. What is important is that you must have a long-range correlator in a theory. If you don't have a long-range correlator, you must have a long-range correlator that is not dying with a distance. Because if you don't have a correlator that is not dying with a distance, you will not be able to, just by locality, how can you have, how something on a boundary can have a local effect on physics, right? Okay, so now, who was here this correlator? Well, this correlator here is obvious who it is. It's the electric field massless. So this correlator, this is a long distance correlator. Why? Because this is a long range correlator. Because it
Should be one over a box there.
no, this is a correlator I wrote. Yeah, this correlator, sure, yeah. So this correlator behaves like 1 over box. That's right. That's what you meant. Yeah, in other words, for p going to 0 limit, this correlator has a pole at p square equals 0. Okay, which is the same thing as 1 over box. Okay. Now this correlator. So this is one condition, that there is a correlator which is long range. And this correlator should be sensitive to the sources which are codimension 1. Because if correlator, for example, massless photon in 3+1 dimension cannot do this job. Okay? If I put charge at infinity, locally somewhere, right, it will not have a physical effect on local physics. Why? Because despite the fact that photon is massless and the correlator behaves like 1 over p square, the source is not codimension 1. So it dies off as 1 over r, let's say, right? So normal Coulomb law, it dies like 1 over r, okay? So these two things are important. And here this is satisfied. So in other words, there is a long-range correlator, okay, the massless field, and it couples to codimension 1 sources, because charges in 1+1 dimension are codimension 1, okay? Now we want to understand the same thing, okay, in QCD, okay? So, because you said instantons. In QCD, absolutely correct, right? So instantons are perhaps one definitely, they are one source that mediate. Yeah.
So I just want to recap what you said. We choose the vacuum, we choose the boundary.
Yeah.
Then we look at the quantum corrections, right? Like this basically quantum fluctuation, which can be non-local, and they are responsible for this kind of behavior, right?
Which part are you asking? Which part are you referring to? The theory without fermions, or
no, with fermions.
With fermions, okay, sure. With fermions, the theory changes dramatically.
We have two integrants. First, the vacuum, which sends the bond, and the second is quantum correction.
Absolutely, yeah, it's precisely the point.
But this is only we can see in this effective action.
No, you can also see like this. That's what I'm saying. That's why I'm offering you 3 different ways to understand the same phenomena. You can choose whichever you like. They are all equivalent.
Then I don't understand how this non-local affects the inter if you're not using the gamma.
No, first of all, let's not use language non-local. There is nothing non-local here. The theory that we started is perfectly local. We get transverse projectors whenever we integrate out massless particles. That's not a sign of non-locality. That simply means that you have integrated out something massless. And that's perfectly fine. That's perfectly manageable.
But then you introduce some degrees
Of course, that's the whole point, because you see, very good. Let's follow your point precisely. Let me restate this statement. So what happened? Before fermions, I had one long-range correlation, okay? And this correlator was making sure that whatever I could introduce as a boundary term had a local physical effect, okay? Right? And vice versa. Okay, vice versa, it looked trivial because you say, okay, who cares? Of course, I can have a constant electric field. But here the point is that this same constant electric field you can interpret like a boundary term, effect of the boundary term. Okay, now then we saw that whenever we introduce either a fermion, massless, or a Stuckelberg in one representation or the other, or introduce fermion in bosonized version, okay, or took into account anomaly because of these fermions, we got that this correlator got killed. Now, this is absolutely natural because to kill a long-range correlation, you need to introduce someone massless, right? Because you cannot kill long-range correlation by someone that is heavy, because I can always go into low-energy theory, much below the mass of that object, and I should be left with my long-range correlator again, okay? So it was absolutely crucial that you had a massless fermion in a theory, and that fermion neutralized your electric field, okay? Fermion or a Stuckelberg, doesn't matter. Stuckelberg is a degree of freedom, but doesn't have its own mass. It's not getting mass from anywhere else, okay? By the way, since you're asking this, let's do a little exercise here. Okay, let me. So we introduced this thing, right? And as we showed yesterday, on this language you also immediately see that f is 0, okay? Right, in the vacuum. And we said, how do we see it? Because if we do variation, we have an equation, d mu of a. Okay, let me put fa. We had a decay constant yesterday introduced, right? Fa, but let me put it to 1. Okay, everything is 1. And then we had second equation for box A plus F. Okay, then from here we integrated out F. This was plus arbitrary theta, right? And we plugged back here and we saw the following thing. That first, the vacuum is A equals minus theta, means that F equals 0 always, so the electric field is screened. And secondly, A is massive. Okay, right. Now let's see what would happen if instead I would add a small mass term for A, its own. Okay, right? So let's add a small mass term for A itself. All right. Of course, if A is a phase, in reality we have to add some periodic function. Okay, so I should add some cosine or whatever, but for this discussion that doesn't matter. I'm expanding around small a's. What would happen? Well, you see what would happen. The first equation would go unchanged. The second equation would acquire an increment. Okay? Now, I again integrate out F, plug it back here. What do I get? I get that, I get A plus theta plus m square A is 0. Where is the vacuum of this theory? It's no longer at minus theta. It's shifted, right? So where? So the vacuum of this theory is now at minus theta 1 plus m square. Right? Now if I take this and plug it back there, I will get that and F is no longer 0. What are we witnessing? What is the effect? Well, the massive field cannot screen the electric field all the way to 0. That's impossible. If it's light, it can screen it a little bit. Okay? For instance, smaller is m, as you can see from here. Bigger theta I can neutralize. But there is always a limit. I cannot go below in arbitrary infrared. Okay? So this is what happened. Now, this is exactly, by bosonization, you can check that this is exactly equivalent of introducing a massive fermion. Again, the same story. Massive fermion cannot screen the electric field, cannot give mass to a photon. Okay? Okay, so now let's move to otherwise we will stay forever in 1 plus 1 dimensions. Let's move to 3 plus 1. Okay. Let me see.
If we didn't understand 1 plus 1.
Huh?
If we want to understand 1 plus 1, it would be useless.
I don't think so, because you can always, you see, that's not the way normally understanding works. Because sometimes you don't understand something in 1 plus 1 and you understand that in 3 plus 1 and you say, oh, wait a minute, this was what was happening there, right? So it's not that you should live in 1 plus 1 until the end. No. We should think in parallel. All right, so now let me see. Now let's fix the order. So first of all, yeah.
Where does the first differential equation come from? I mean, if
I did variation with respect to A mu. Of course, this is F is just it depends on A mu obviously, because again F I erased it. F was 1/2 of epsilon mu nu F mu nu, and A mu was here. So right, so d mu A nu and right. Okay. Now, so now let's see the story in 3 plus 1 dimensions. So there are few things that I have to remind you about 3 plus 1 dimensions. Now, first of all, before I go to the standard story and confront this with the standard story, let's ask the following question. Let's go to QCD, okay, in 3 plus 1, QCD. And let me for a moment assume that all the quarks are massive, sufficiently massive, okay? So then in this theory, we have a QCD scale, okay? So now this theory is a theory with a mass gap all right? Which means that all the propagating degrees of freedom are massive. And it has a high energy story and low energy story, okay? So the high energy, and I will use these high energy and low energy observers all the time. So observers or physicists, let's call them Alice and Bob. So Alice is a high energy observer. Bob is a low energy observer, okay? Observer or a physicist. They know physics. They are not passive observers, okay? Now, for Alice, so this is Alice. For Alice, degrees of freedom are quarks and gluons, okay? And for Bob, degrees of freedom are pions, colorless objects, okay? Now, in this theory, when we move from high energy to low energy, two important things happen. More things happen, but two are important. The two are most important at the moment. Maybe three are important. Anyway, we'll see. So one is confinement, right? So the theory becomes confining. We hit the strong QCD coupling, and below that scale, confinement takes place. Which means that asymptotic states are colorless states. Deep infrared, large distances, we see colorless states. So therefore, Bob is thinking in terms of colorless objects, okay? He's formulating his description in terms of colorless objects. This is one thing that is happening. And the second thing is happening if fermions are sufficiently light or massless. A chiral symmetry breaking takes place, okay? Now, for a moment, let's assume that fermions are massive, okay? So we come back to chiral symmetry breaking in a moment. Now, fermions are massive, and now we are in QCD. So Alice knows everything about instantons, theta vacua, everything is fantastic. So she wrote a term in the Lagrangian, and she knows that this term is a declaration of her choice of the theta vacuum, okay? Now, she knows that theta is a boundary term. And she also knows why this boundary term can give local observable physics because of instantons, as you said. Okay, so there are instantons, blah, blah. Fantastic. Now, what about Bob? Bob, so when we move from high energy to low energy, at some point Alice and Bob, they meet. Alice gives all the information to Bob. Now Bob has to continue to describe the theory. And Bob knows that there is a boundary term, okay? But how can Bob understand the fact that this boundary term gives a local effect? Because Bob knows nothing about instantons. Because Bob only thinks in terms of colorless objects, okay? Right? So Bob is in a theory below the mass gap, right? Now, if you are an observer in a theory below the mass gap, would not you think that you don't have any degrees of freedom? Nothing. So nothing can penetrate from boundary or whatever to you. It's not the logical thing to think, right? Then what is happening? Is there some kind of a miracle or what? That Bob is in a theory in which to excite every single quantum costs energy at least lambda, okay? Right? So this means that if you ask Bob, all the correlators in this theory should die off exponentially at large distance, because that's the property of quantum field theories with the mass gap, right? All the correlators die exponentially, right? Okay? But that cannot be, because there must be a correlator which is long range, that and which makes this effect of theta locally physical, okay? And indeed, in QCD there is such a correlator. And that's why Bob and Alice, they can agree on discussing physics, okay? Now, this correlator is called topological susceptibility of the vacuum. You probably saw it an infinite number of times, right? Sorry? Topological susceptibility of the vacuum. I mean, but by the way, that's how people calculate axion mass and etc. etc. It's through topological susceptibility. So this quantity is extremely important. Now, so this is a correlator. Sometimes people call it Q. This correlator we define as a long distance limit, or Q going to 0 limit, limit Q going to 0 of a okay, so which is I will explain who is who. Sorry, here and here we have IQX. Okay, so this is a low energy limit. Since we are interested in the vacuum structures, we are interested in deep infrared phenomena. Okay, so this is a 0 momentum limit of the correlator. Okay, so now this is topological susceptibility because of the obvious reason, because FF dual is topological, right? So now FF dual you have seen many times, but let me just remind you what the notations are here. So FF dual is a dual field strength, right? So it's okay, dual field strength. So F is the normal non-abelian field strength of a QCD theory. So for simplicity, we can consider SUN color QCD with SUN colors. Doesn't have to be 3 necessarily. I will not discuss large N QCD. I mentioned a couple of times a few important things like Witten, Veneziano, mass generation of eta prime, but will not discuss in details. Okay, so this is the story. Now, obviously, it's gauge invariant. Okay, it's parity odd. Now, A mu is a gluon. So this guy depends on A mu. Let me introduce A mu. A mu will be a gluonic matrix. Okay, so A mu means this is simply all the gluons convoluted with generators. Okay, and these generators, they have IJ indices. So SUN generators. Generators, of course, transform in a joint representation, but they are written in the fundamental one here. Okay. Okay, so these are matrices, A mu's. Okay, so now. And this is the correlate. Now, since this is, we call it topological because of obvious reason, because this is Chermpon-Tragin density, topological density, FF dual. Okay. Now, you can see immediately that somehow this quantity smells instantons, because, as you know very well, instantons are precisely ones that are given with this topological charge density. Of course, instantons are not Minkowski configurations. They are Euclidean, right? They describe transitions between the different winding numbers, right? Topological numbers. They change topological winding number. Now, but Bob has no instantons whatsoever. Okay, so now this object, of course, it's a colorless object. So therefore, it's fully legitimate to be part of Bob's theory of description. Okay, so Bob can use for bookkeeping any colorless object. Okay. In his theory. All right, now, okay, so now let's ask this question. Okay, fine, there is this correlator, but what do I make of it? Okay, so now in QCD without massless quarks, this correlator is non-zero and is constant. It's a pure number. By the way, the story about computation of this correlator is a whole story, okay, right? But in my lectures, I will assume, yeah. Huh?
Where it is not 0 there?
No, this is simply a number. It's independent of anything.
Where it's not 0? You said,
what do you mean where? You mean in QCD without massless quarks. We are working in QCD without massless quarks. Without massless quarks, without axions, without Stuckelbergs. Pure glue plus heavy quarks. Okay? And so this is a constant non-zero. Okay? So we call it Q.
Massless?
Yeah, we'll see what happens if quarks were massless. That's the part of the story, of course. Dramatic things happen when quarks are massless. No, he doesn't have to write. He knows that there is a quantity, colorless quantity. This is the object. So Alice can give Bob this object, okay? And that's it. Just don't resolve it. It's like a black box, okay? No, I'm not saying that Bob doesn't know QCD. Of course he knows QCD. He just operates in terms of the gauge, the color blind quantities, okay? Only measures color blind quantities, let's say, okay? Okay, so now, one more thing. This object, you can very nicely, I don't know, maybe I should use space here. So this object, you can rewrite as an exterior derivative of a 3-form, okay? Now, this is a famous 3-form. It's called Chern-Simons 3-form. You have seen it infinite number of times, probably, okay? So the 3-form has the following form. It's an anti-symmetrized form out of gluon field strength. Of course, you have to take the trace because these are matrices, and so it's A dA alpha beta gamma minus 2/3 of A alpha A beta A gamma, okay? Anti-symmetrized, okay? Now, okay, this is just rewriting, but actually it's more than rewriting, because again, C is a colorless quantity. So from that point of view, but it's not gauge invariant, okay? What is gauge invariant is exterior derivative, but C itself is not, okay? Now, since this is invariant, you can already guess how C transforms under gauge transformations. So when I do QCD gauge transformation, C has to shift as an exterior derivative of a 2-form, okay? And you will, so, okay, this is a nice exercise you can do just to explicitly derive these 2-form in terms of QCD transformation matrix, okay? So SUN transformation matrix. When I do SUN transformation, A is transformed, right? A is transformed in the usual way. And so this form shifts. So C shifts as an exterior derivative of a 2-form. Now, this 2-form, of course, depends on the SUN parameters, okay? So, as it should be, so C is a fully fledged 3-form, the type that we discussed in our previous lecture, okay? So therefore, let's summarize what Bob knows. Bob knows that there is a correlator. Now, okay, so in other words, you see immediately that since FF is D of C, right, derivative of C, the fact that this correlator is constant means that the correlator, analogous correlator of C, has a pole at Q square equals 0. Okay? Now, this means that C is a 3-form that can mediate a long distance information. Okay? Now, since C is a 3-form, we have to first understand, okay, first let's try to understand what's the physical meaning of C, right? Now, so what does Bob know about C? Bob knows that there is this object, okay, which has typical properties of a gauge 3-form C, and it looks massless, this C. Now, the question, I mean, is this C, but C is a composite operator. It's composed out of gluons or whatever, right? Does this matter for Bob? The fact that in the original theory, when Alice gave this operator to Bob, Alice knew that it was composite, and Bob also knows that it's composite. But does it matter? No, it doesn't matter. Because the fact that CC correlator has pole at Q square equals 0 means that C as an object, from the point of a low energy observer, Bob, okay, contains in an operator expansion contains a massless free form plus all possible massive garbage. Okay? In other words, C, so it is extremely important to understand. It doesn't matter whether I gave you as this operator as a composite or not. The moment the correlator has a pole at q squared equals 0, moment you are in a theory with mass gap, you know that this C at low energies will behave practically as if it's elementary. Okay? It doesn't matter that it was composite at some high energies. Okay? Because of two reasons. Because theory has a mass gap, okay? And there is a pole at q squared equals 0. Now we can do this explicitly. We can do this. I don't have time to do this, but we can do it explicitly. Well, you can do the following. You can introduce external sources. So what's the way to check this statement, right? So in other words, first of all, the statement, as I said, statement means that as an operator, C contains a massless free form C plus some heavy stuff, okay? Now, I give you this type of object, okay? And I will ask you to write down an effective theory of this at low energies, okay? Now, you can do the following. You can now introduce a probe sources for this object, some probe sources, whatever you want. These probe sources could be fermions, bosons, composite operators. And then see what kind of interaction this C form mediates among these sources. Okay? Now, of course, whatever interaction this C will mediate will be such that at large distances, only this part, the massless correlator, will survive. Okay? And so, which means that the effective theory of these sources, after integrating out the form C that you can write down, will be an effective theory that you would obtain by normal elementary three-form field. Okay? With whatever action which you will specify. Is this clear? This is the power of low energy thinking. Yeah?
C and C, so which one?
Yeah, I denoted with the same symbol. I don't know, C0.
But which one we measure, which box we measure?
Yeah, that's why I'm saying that. So, in other words, okay, let's go.
He actually wants to see the C.
Only these measures at large distances, because for the vacuum structure.
How he measures only locally, right? So he has something like that, collider or something, and he wants to see the C0, right?
No, you mean there are several things that. Let's separate the story. So first, I'm trying to construct an effective theory of this C. For that, I can introduce in theory a probe sources, write down the effective theory, then get rid of those sources.
Yeah, it was an analogy that we in previous classes we also observed this kind of thing. Like some parameter goes 0, we see some here.
Sorry, I don't understand this. So could you repeat?
My question was.
Yeah.
So this guy, he measures things locally.
Yeah, of course.
But how this big scale things will affect his measurements?
No, are you asking his measurements in real QCD or his measurements in this probe theory? First, he wants to write down effective theory. First, I want to convince you that we are going step by step, right? So the first step is that I want to convince you that because there is a pole in this propagator at q squared equals 0, okay, this means that in q going to 0 limit, of course, massless one dominates. Of course, you have extremely complicated structure of this correlator. This correlator will have some mass. What I know is that all this mass is unimportant and q going to 0. Okay, so now the correlator we can always spectrally expand in quantum field theory. Okay, and this is effectively the information that we get from the spectral expansion. In other words, this means that this fact means that C contains a massless field plus all possible massive modes. Okay.
Is there any analogy with this, for instance, massive photon that we look in previous classes?
There's no analogy for massive photon. There is an analogy for massless one.
With C0, it is basically massless photon.
Exactly. That's it. C0 is a massless photon.
And then this with this Stuckelberg, can we identify this sum of the Stuckelberg?
No, there is no Stuckelberg for a moment. We are going step by step. We are, for a moment, in a QCD without, in QCD with mass gap, and that's it. In QCD with mass gap, we are trying to understand, rethink this long-range correlator in the language of a three-form. Okay, right? That's what we are trying to do. Okay, so now the information that we have is that the correlator has a pole. What I'm saying is that this means, in quantum field theory, this means that your low-energy effective theory will be a theory of a massless three-form plus some massive stuff. Okay, this is one statement. Now, as I said, to convince you that this is a normal theory, you can do the following thing, which will be obvious, that you can introduce probe sources. Now, depart from QCD, introduce some external sources, which artificially would couple to this C, do all possible measurements, and get convinced that at large distances, these sources would behave as if they are mediating the force with each other through a massless three-form C. Okay? So in other words, this means that an effective theory below
This is low energy.
low energy theory. We are at energies below QCD. We are interested in the vacuum structure. That's our power. Because since we are interested in vacuum structure, everybody that is heavy is gone. They will not contribute. Okay? This is the power. So in other words, let's make this materialize this in so this means that effective Lagrangian, that Bob, okay, let's call it Bob, that Bob can write down, will be the following Lagrangian. Lagrangian of this C, okay, I don't know what to call it. Let me call this C and this, I don't know, C original or something. I don't know, C original. All right. Okay, so now, Bob will write down Lagrangian. Now this Lagrangian by gauge redundancy. Now here we are exploring the full scale, the power of gauge redundancy, because we know that once I have a three form, I know what kind of action it can have. Okay, by gauge redundancy. So the action will be some k function, algebraic function of the field strength. So the field strength of C, we can define it as F alpha beta gamma, this FF, which is the same thing as FF dual, right? Sorry. But we can also write this F as epsilon tensor times a scalar. Just exactly the same way we did it for in 1 + 1 dimensions, okay? So then there will be algebraic function of this F and high derivatives. All possible high derivatives, okay? So all possible high derivatives suppressed by the scale in your theories. So QCD scale, or scale of quarks, heavy quarks, etc. Okay. So these terms will have the form, for instance, I don't know, some f box f square over some whatever box plus lambda square in whatever power, in whatever part, okay. Now these terms, they come from integrating out all possible things like this. Also other story, other massive states. Okay? That's it. There is nothing else, because there is nothing else in Bob's theory. There is nothing else that matters at long distances. Okay? Now Bob wants to stare at this and find the vacuum of the theory. Okay? What's the vacuum of the theory? So we do variation with respect to C, and we find that the vacuum equation, and we're looking again in deep infrared. Now that's the advantage of this deep infrared, because all this garbage dies off. it doesn't matter, cannot affect the vacuum structure, okay? Because vacuum structure is by default a zero momentum limit and zero energy limit. So therefore, so this will be K prime, where K prime is simply derivative of K with respect to F. Zero, okay? Which means that unless K is singular, has some crazy singularity, the vacuum is characterized by a constant F, exactly in the same way is 1 plus 1 dimensional QCD, okay? Sorry, in QED. So therefore, there is some F constant, and this F constant I can call theta. Or
This is still related to K, this
related to whom?
to K prime?
No, the K prime, so this is an algebra, so in other words, yes, sorry. So this is the solution, right? If you want. Okay, so there is some constant, and this is now an algebraic equation.
It depends, yeah.
Yeah, so this is an algebraic equation on F, and it's solved by some constant F, whatever it is. Now let me take this F constant. I can take this F constant, plug it back into and expand now around this constant my theory, the way we did in 1 plus 1 dimensions, right? So if I do this, then my original theory will have first term, which is linear in F, and I denote the coefficient by theta, okay? And then high order terms, F square and the high order terms, okay? And the same story, literally. So now Bob understands why there are these theta vacua in the theory. Because the way Bob understands theta vacuum is this. There is a boundary term, which you could understand as a boundary term. Why is this boundary term important? Because there is a correlator, because there is a massless C form in a theory. Now, it is extremely important that it's a 3 form. Because 3 form is the only object that can couple to codimension 1 sources. And this was extremely important, because anything else that would couple to codimension, let's say codimension 3, massless photon, would not change the story, okay? This is the point. So in other words, you see what happens is that all the song and dance by ultraviolet physics, or at least by physics that is known to an ultraviolet observer, okay, such as instantons. Now, instantons are not necessarily ultraviolet, as you know, they are scale invariant. That's why precisely they managed to do this, right? This gets effectively summed up in in existence of a massless 3 form in theory of Bob. Okay, so from Bob's point of view, theta vacua are simply vacua characterized by different values of the electric field of this 3 form. You can always interpret them like this, okay? Now, it's exactly the same story. I don't know, maybe probably I'm wasting my time repeating it, but okay, the same thing. We can always recast this as a boundary term, right? This is, we can always think of it as a coupling of...
It's already given, so it is exact number, so it's not that parameter, right, for the ball.
No, once you chose it, it's an exact number. That's it.
I mean, Alice will choose it, right, but Bob is not, so he can actually measure it, right? And
both can measure it. I mean, there is no problem with measurement. I mean, Alice can also measure it using heavy stuff. Yeah.
Can you explain again how to exclude the term like propagator like term which you erased?
Oh, you mean the high derivatives?
Yeah.
No, they just die at low momenta. That's what I'm saying. I mean, high derivatives, the high derivative terms, they are nice because they never contribute into the vacuum structure of your theory. This is a universal property of high derivatives.
even for QCD case?
For any case, who cares if it's QCD or not? Well, high derivatives, I mean derivatives scaled by some power of the scale. In other words, these are terms that you are getting by integrating out heavy stuff. Or you don't even have to talk about derivatives. Look, you have things that you are getting by integrating out heavy things, right? And those things that you are getting by integrating out heavy things, the ones that contain, remember, fluctuations of heavy things, they will decouple from the vacuum structure, okay? Only the things in which only light things appear without extra derivatives, they will survive. And that's the universal problem. That's why we can study the vacuum structure without worrying about high derivatives in the standard model, for instance, right? Because otherwise I could ask the same question. For instance, you tell me, in the standard model we have a Higgs effect. And the vacuum of the standard model is the vacuum in which W and Z acquire mass, right? Then I can tell you, how do you know that? Because can you control infinite number of high-dimensional operators? Yes, you can, because they do not contribute into the vacuum. That's why, that's exactly the point, yeah. No, let's clarify your confusion. What's the problem?
I was just confusing this high derivatives with renormalization.
No, this has nothing to do with renormalization. So this is simply a fully fledged effective field theory understanding of what happens in the deep infrared, right? Okay, so now, where are we? I wanted to write this as a current, just for completeness. So this couples to a current, right? And this current is a boundary, again, it's the same story, no? Theta, D for X, D for X, delta, theta D3 Xi, delta 4 X minus X mu, dx mu, dx alpha d psi A, dx beta d psi B, dx psi C, and plus epsilon tensor here, ABC. Okay, so this is just a boundary. So it's like a two-brane. Okay, so now. Okay, very good. So now the question is, now what happens? When we introduce quarks, so now let me introduce massless quarks, okay, in the theory. And when we introduce massless quarks, picture changes dramatically. Notice again, we are going sort of in analogy with 1 + 1 dimensional QED. There we introduce massless fermion, okay? Here I'm introducing a massless quark, one or many, doesn't matter, okay, at this point. And the picture changes, and let's see how it changes, okay? Now, let's see. Now, so the first is the standard story, right? So what is standard story? So standard story, we have QCD scale. Let's introduce a certain set of quark flavors. So this we can introduce as so flavors normally we call fermions in fundamental representation. So we can introduce them as left-right pair, left-handed and right-handed, transforming in the same representation, or both left-handed, for instance, transforming in the opposite representation. Okay, so instead of introducing right-handed fermion, we can always introduce a left-handed anti-fermion, right? So in that case, we can be in the basis in which they are both left-handed. So for instance, in that basis, we can introduce a notation. We can have fermion psi. We can give a flavor index J. It's not a color index, a flavor index J. And then we have anti-left fermion with a flavor index J bar. Let me call bar on top of the index, flavor index of that. Okay? Both are left-handed. And so they are massless. Okay? So what do we have here? We have a flavor symmetry. Global flavor symmetry on top of color symmetry. So now the symmetry, there is a gauge group SUN color, but there is number of flavors. Okay, let me take them to be NF, and there is a flavor group, flavor symmetry, because we can rotate left and anti-left independently, and so there is a flavor group UNF. Let's call it UNF left, UNF right, or sometimes it's useful to write it as UNF left, SUN F right, times U1 vector and times U1 axial. Now, so SUN are clear, vector and axial are also clear, so vector is the symmetry under which, in this basis, where they are both left-handed, they transform in the opposite way, okay? And the axial is in this basis when all of them transform in the same way, okay? So under the axial symmetry, they all the fermions, psi tilde, they go to some I alpha psi tilde, okay? This is the axial symmetry. Okay, so now, what happens in QCD, just so let's refresh our memory. So what happens in QCD is that there is, on top of confinement, there is a phenomenon of chiral symmetry breaking, okay? So QCD vacuum chooses to deliver an order parameter which spontaneously breaks the flavor symmetry, okay? Now this order parameter is fermion bilinear, and to follow Toft's notation, we can introduce effective scalar order parameter defined as fermion bilinear. I think Toft introduced it like this. I'm sorry if I'm wrong. Okay? Now, what do we know about QCD is that this order parameter acquires an expectation value, okay? Acquires an expectation value which is unity, universal in the limit of massless quarks, okay? So this expectation value of is proportional to delta, okay? Times a scale, of course, some V cube or whatever, all right? And which means that it is breaking symmetry which means that it is breaking the flavor symmetry down to a diagonal U1 vector, sorry, U and F vector. So in other words, this order parameter, so it's proportional to unity, right? So it's 1, 1, 1. So okay, again. So this order parameter transforms as bifundamental, okay? So it transforms as fundamental representation on the left flavor group and as fundamental on the right flavor group, okay? So the original Lagrangian is invariant under independent rotations, but the expectation value is only invariant under locked rotations. So the two rotations get locked. Now if I simultaneously transform left and right, then I can leave this invariant, okay? So that's the group that is broken. Now let's call this not vector, actually it's not vector. Let's call it L plus R, and this L plus R is S to NF L plus R plus U1 vector. So this U1 vector survives unbroken. Now the part that is broken is the chiral part, okay, which rotates them differently, and the U1 axial. Okay? My time is finished, or like another 5 minutes, something like that? Is okay? Okay, so now what happens? What happens is that because of this breaking, okay, by the way, why this breaking happens and how to understand it from the first principles is a whole separate story, absolutely fantastic. So here we are taking it for granted for a moment, okay? Now, the result of this breaking is that you have Goldstone bosons. Okay, so Nambu-Goldstone bosons that in real QCDs are pions, kaons, etc. Right? Now, in the limit of, and you know that historically there was this U1 puzzle. Okay, U1 puzzle was related precisely to the fact that one Goldstone boson, pseudo-Goldstone, of course they are not Goldstones in real QCD, they are not Goldstones because quarks are massive. So pions, kaons are massive. And, but however, one pseudo-Goldstone was missing. Okay, at low energies was, so this problem was called the U1 problem. Okay, this problem was solved by Toft, who showed that this missing Goldstone boson is eta prime, and he also explained why eta prime is much heavier than not much, but why it is heavier than the rest. And of course, this is also central to our story here. Now, the reason why eta prime is heavier than the rest has nothing to do with quark masses. So we can continue story with massless quarks. Okay, so we have very nice massless quarks, and there is one Goldstone boson which corresponds to this U1 axial, which I will call eta prime because of the obvious reasons. And this eta prime Goldstone boson is getting mass through Toft mechanism. Okay. Now, what else we have to remind from the standard picture? Okay, yeah. So now, how this U1 prime is getting mass in Toft's description? Okay. There is another description in large NC QCD by Witten and Veneziano, and which I will not touch. Okay. Because of, it's a beautiful story, but okay. Let me first describe this. So now, how can we understand the fact that this U1 Goldstone boson eta prime is becoming heavy? Well, Toft's point was that this U1 actually is anomalous. Okay, and because it's anomalous, instantons are permitted to generate mass for these objects. Now, how the mass generation happens? There is a very nice way in terms of order parameters and effective potential to understand this. So the point is the following, right? So let's think in terms of effective potential of this order parameter. Okay, so somehow, let's say we don't know how. This is Bob, territory of Bob. Okay. There is some effective potential which depends on this order parameter. Now, this effective potential will probably contain infinite number of terms. Okay, it will be very complicated, but it contains finite number of invariants. Okay, there are only finite number of invariants that you can build out of this order parameter. I mean, finite number of invariants with respect to the original group. Okay. Now, of course, this order parameter is colorblind, but you can build. But it has flavor indices. Okay. And what can you do? You can take traces, right? So out of this order parameter, you can build invariants by taking traces of phi and phi conjugate. Okay. So, for instance, I don't know. So trace of phi dagger phi, trace of phi dagger phi and so on. Okay. There will be finite number of invariants. Who will tell me how many? At least order of magnitude wise. How many?
How many we can construct?
Yeah, if I have a group which is I have a bifundamental with respect to the group SU and F, left and right, right? F square. NF square. Why square, not something else? Well, notice that, you see, the guideline is the following. Okay, take this as an exercise, but the guideline is the following. Notice that already the number of components of this guy is how many? It's a bifundamental, right? It's NF by NF matrix, right? So how many components does it have?
Is it symmetric?
No, it's bifundamental. It's not symmetric over there. It's literal transforms is bifundamental. N and NF, NF, right? NF, NF bar. N square, right? n square parameters. So, right. However, we can, not all of them are independent because of the symmetry, right? So you can use symmetry to bring it to a simpler form. In particular, for instance, diagonalize it. Okay? Right? Now, since the invariance should not change under symmetry transformation, this means that invariance cannot carry more you cannot have more independent invariance than the number of components that you can to which you can bring this bring this matrix. Okay? Anyway, okay, think it through, but it's very simple. But yeah, anyway, so the point is that there is finite number of invariants, and so therefore this will be some complicated function of this invariance. Okay, now, by the way, if you play around with this invariance and write down some complicated function like that, no matter how complicated, actually the analysis of the minimum is not so complicated. You can see that there is a huge set of parameter space where indeed this function gets minimized for unity. Okay, so despite the fact that it may contain infinite number of terms and look very complicated, you can fish out that there is always this kind of vacuum solution. Okay, so therefore you have this complicated story. Now, the eta prime is a Goldstone boson that corresponds to a transformation of the phase, of uniform transformation of the phase of all the components. Okay, right? In other words, eta prime is a Goldstone boson that corresponds to the phase rotation of the determinant of phi. Okay? Okay, so that's the way we can parameterize it. So this is eta prime. Okay, so when I do U1 transformation, okay, the Goldstone mode corresponding to the change of the phase of the determinant, that's eta prime. Okay. Now you can ask this question. Okay, how could this type of potential generate mass for the eta prime? Okay. In other words, to generate mass for the eta prime, the potential should contain a term that explicitly breaks this U1 axial symmetry. Okay? Right? No other way. If potential continues to respect this U1 axial symmetry, you will never generate mass for eta prime. So you see, whatever physics, instantons, whatever song and dance is there, they should sum up into an effective term in this potential, which explicitly breaks U1 axial symmetry. Okay? Now, what kind of terms can we write down? Okay, that break this U1 axial symmetry. And actually, Toft anomaly matching is a very nice, Toft anomaly consideration is a very nice guideline, because we can notice that since this is generated through instantons, okay, by assumption, we are working on an assumption the instantons are generating it, right? And they are generating because they are permitted, because symmetry is anomalous. But this anomalous symmetry has an anomaly-free part. There is a discrete subgroup of this U1 symmetry which is anomaly-free. Who remembers what is this discrete subgroup? There is because it depends on the number of flavors. I'm sure you heard it in the axion lectures, because also it enters in this axion potential. There are NF flavors. Right? Yeah, Z. It's always Z something, sure. yeah, Z, right. Z and F twice NF or something like that, right? Okay. Yeah, so there is an anomaly-free subgroup, Z and F, okay? That is sorry, this is here. Okay, which is respected by the by anomaly. Okay, so it's anomaly free. So therefore, the explicit violating term should be such that it respects this symmetry. Okay, so the NF symmetry that acts on this phi should be respected. Then it simplifies a lot the search for the invariance, because it must be invariant with respect to the rest and invariant with respect to the NF symmetry, and that's actually determinant. Okay, so determinant has this property. Not determinant conjugate. Determinant conjugate, this would respect the entire U1. No, it should be only determinant. Okay? Only determinant or powers of the determinant. Okay? Not multiplied by conjugate. Okay? Okay, so this means that this potential can contain whatever which delivers this thing, but then must contain something that depends on the determinant. Okay, and this is called top determinant, right? This. So therefore, this potential contains determinant of phi.
Determinant of phi.
Yeah, of course, will be determinant of phi star, and so on. Okay, that could contain higher powers, etc. Now, this determinant, we can see immediately that this generates mass for eta prime. Why? Because eta prime is simply a phase of this determinant, okay? And you can see now we can write it down like this. Okay, so now the toast point, as you know, was that once I integrate instantons, I generate this. Actually, we know that you generate this. Okay, until here, we didn't have to employ instantons. Until this point, we had simply symmetry considerations. Okay, now we need a source which actually will actualize this term, will really generate it. And this is shown by Toft. This is generated from the instantons. Okay? And the instanton generate term with the coefficient. So, okay. So we get term generated for the instantons. There is with theta and determinant of phi. Okay? For this consideration of eta prime mass, theta is not so important at the moment, but okay. Now, and we can write this down as exponent I eta prime over f eta prime and the modulus of the determinant. So the moment I give expectation value to this order parameter, okay, this will generate a term like this, okay, for the phase of the determinant. And this immediately generates, okay, this immediately generates here a cosine, right? This generates cosine type potential. Of course, with a coefficient that you have to compute, okay, at the end of the day by doing explicit computations by instantons. Here we cannot get away without explicit computation. I mean, we can make a guess that for small number of colors, this is given by around the QCD scale, but we have to do. You need to do computation, and this is part of the challenge. Okay, but we see immediately how the eta prime must get generated. Okay, so now I have to finish probably. I don't know. Yeah, let me finish. Okay. Yeah, because I want you to make a comment, but okay, this comment. Okay, now notice that this eta prime behaves very much like the field in the 1 + 1 dimensions that was canceling this electric field. This eta prime cancels theta. Okay. Now there is a very good reason for it why eta prime cancels theta, and we'll continue to discuss it in the next lecture or something like that. Okay. Yeah.
An analogy between what we did in the QED with the screening and gravity.
Oh, that's a fantastic question. Yes. Sorry. So the question was if we can have an analogy between the screening of the electric field that we had in QCD and whether there can be something like that in gravity. That's what you're asking, right? Now, obviously, this cannot be in Einstein gravity. It has to be in massive theory of gravity. Okay. Now, yes, at the linearized level, that is true. At the linearized level, if I introduce a mass for the graviton, this is so-called Pauli first theory, and if I couple it to a source, then you can see that the source degravitates. So we even call this name. We use the name degravitation. My collaborators and I for this effect. So that is true. So it source degravitates. And this is true for not just for gravity, for any, as I said. Any theory which propagates massive degrees of freedom can no longer generate long-range correlations, and so any source will be sooner or later screened. So typically, sources will be screened at the distances larger than the Compton wavelength of your field. Okay, so that is the same is true in gravity. Now, so yeah, from that point of view,
but this massive graviton would be like a UV completion of the Einstein theory, right? Because in Einstein theory, is graviton considered massless, right?
No, in Einstein theory, graviton is massless, right? But now, if graviton, no, this is a question, general question. A lot of people are thinking about it. There is even a model by, there is a model which sort of looks like goes free, highly nonlinear, the Ram-Gabadadze-Tolly model. So anyway, so this started with Pauli Fierce, people and people like Deser, etc. So, but why you say that it's ultraviolet completion? It's other way around. It would be an infrared modification of gravity, because there was a discussion in the previous lecture, right? So that the graviton, if it has a mass, is much more severely constrained than the photon mass, paradoxically. Despite the fact that photon we measure in laboratory is much stronger interacting, the mass of the graviton is much stronger constrained because of cosmology, and the graviton mass cannot exceed the Hubble scale. Okay, so it has to be less than the Hubble. So that's an absolute bound, because otherwise we would see modification of cosmology. So graviton mass has to be less than the Hubble. Hubble today, okay. Yeah, so and the reason for this also is that gravity doesn't have anti-charges. You see, in electrodynamics you have charges and anti-charges. For a free form you have branes and anti-branes. Gravity is something that doesn't have anti-charges, because there are no sources with negative mass. Theories with negative mass make no sense. And so therefore there is no screening of gravity in the same sense as screening of electrodynamics. For instance, no vacuum polarization or anything like that in the same sense, but there can be some analogous effects in these modified theories of gravity, etc. Okay? Yeah. All right.
Let's go to lunch.
All right, let's go to lunch.